Hi class. So in the last video we talked about bifurcation theory. So we were able to classify different types of bifurcations. So these are the points where if you have a first order difference equation that is dependent on both your x value and some adjustable parameter r, we're interested in understanding how the stability of fixed points in m cycles changes with r. So to illustrate this, we're going to use the discrete logistic equation. So this is the dimensionless discrete logistic equation that we approximated a couple videos ago. And we're going to plot it with several different values of r to see what happens. So the first thing we can do is we can try cobwebbing on several different parameters of r. So in the code below, I've listed out these two parameters to change at the top, so r and your starting value. And I suggest trying out several different values from 2 to including 2.75, 3.1, 3.5, etc. Because as we saw in the last video, this controls how many stable fixed points you have. It controls what the stable fixed points are, as well as if you have stable 2 cycles or 4 cycles or 8 cycles. So let's start by setting this to 2.75. So what do you get? Well, we do their cobwebbing. You have your diagram, and so this is what it looks like at the end, but let's play it and see what happens. So for 2.75, well, if we start at 0.1, it goes up, and then it sort of circles around and comes into this stable fixed point. So as we know, the fixed point x bar here is stable when r is between 1 and 3. And 0 is an unstable fixed point, so it goes away from there. The other thing we can do is, in addition to cobwebbing, we can also plot out the trajectories as a function of time. So let's again set this equal to 2.75. We're starting at 0.1 again, and we're going to do 32 iterations. And this is just a simpler plot. Let me run this. And when we run this plot, you see you start out at 0.1, you go up, and then you sort of oscillate around, but you pretty quickly converge to the stable solution here. And so those are a couple of the things you can show. And so one of the other things you can do is you can plot a bifurcation diagram like we discussed in the other video. So we're only going to plot this around r equals to 1 because it gets super complicated when r gets larger and you get all of the various period doubling bifurcations. But so we're only going to plot around r equals 1, which plots x bar as a function of r. So we first need to solve for the set of equilibria, and we can do this symbolically. And I colored the different lines based on the stability in those regions based on what I already know. And what you get is, when you run this, you get that you have this stable equilibrium, so this is 0, and then it becomes unstable as you pass 1. Here you start out unstable. This r minus 1 over r equilibrium is unstable to begin with, and then becomes stable and positive, and so we only care about it when it's positive above r is equal to 1. And so this here is a bifurcation, as we discussed, and so this here is a bifurcation that swaps types. And so this is a transcritical bifurcation, so type 3. Yeah, so there are lots of different types of bifurcations, and in your exercises I'll have you be doing both some examples here in sort of Python, as well as by hand and understanding the different bifurcations. I should note that I cheated a little bit on this bifurcation diagram. As I mentioned, I already know the stability, and so I could just mark them in different colors. Writing a Python program to plot the correct colors, then for the stability of each of the critical points, or for each of the equilibria and like m cycles, it's actually a little bit more complicated because then you also need to have it symbolically take the derivative and test for stability like that. So we're not going to cover that in this course, though it is something you can do. I think that's about it. Let's go back and try a couple other example values. So I think a more interesting value is when you get sort of doubling behavior. So let's see, I think for 3.5 you get a 4 cycle, I think. So let's see, when we do 3.5, yeah, this gives a 4 cycle. So it's a little bit hard to see, but we start here, it goes up, and then it has to go towards the 4 cycle first. It's a stable, asymptotically stable 4 cycle, so we'll eventually get there. But yeah, here, see? So there's this cycle, which is this point, this point, this point, and this point, but not in that order. So it keeps on going back and forth between those. It's a little bit easier to see if you plot it just the trajectories. Let's plot flat. And so you see, like, there's the cycle goes between this higher one, this lower one, this this very high point, this very low point, this high point, this low point, and then back up to the very high point over and over again. And so that's the 4 cycle that this trajectory converges to. Though sometimes you end up getting super chaotic behavior. So I think 3.8 is an example of chaotic behavior, where things just go every which way and there isn't a nice rhyme or reason. Yeah, so you'll see that this starts going basically everywhere. And the thing about chaos is that if you like change the starting point even just a tiny bit, then the trajectory might go somewhere completely different. So you should play around with that and see what happens. And if we do that here, we get the same thing. So you see it starts going around, and you see there's sort of pseudo-periodic behavior here and there, because the trajectories are moving around, but depending on where you start. So if you start just slightly different, let's say 0.11, then this trajectory actually looks quite different, and you get very different behavior. And so this is an example of chaos at work. I think that ends this quick video. You should play with, I'll make the code for the Colab available, and you should play with lists and just try to get an intuitive sense of what happens at these bifurcations with these different kinds of equilibria. Thank you very much.